Okay, so welcome everyone. Today we are happy to have Pierrick Bousseau joining us from France, and he's going to tell us about refined holomorphic anomaly equation for local P2.
Okay, so thank you very much for the invitation. So today we'll talk about some results which are essentially contained in some paper called Holomorphic Anomaly Equation for P2E and the Nekrasov-Shatashvili limit of local P2, which is joint work with Honglu Fan, Shuai Guo, and Longting Wu. But in fact, this paper is somehow the last step of a long story, which build on quite a number of some of my previous works, which are just listed there for references. Okay, so the general topic is refined topological strings on non-compact Calabi-Yau threefolds. And it's a general physics expectation that refined topological string is expected to satisfy so-called refined holomorphic anomaly equation. And as I will review in my talk, in the case of the ordinary unrefined topological string, this fact starts to be well understood mathematically. And the result I will talk about today is one of the first mathematical results going non-trivially in the refined direction. So what I mean here is starting from a geometrically definition of a refined topological string to show that you indeed produce a solution to the refined holomorphic anomaly equation. And more precisely, we'll focus on one very specific example, the example of local P2, a non-compact Calabi-Yau threefold, which is a total space of the canonical line bundle O-3 over the projective plane. And we'll focus on only one part of the refined topological string, the Nekrasov-Shatashvili limit of the refined topological string. And as I will explain, this limit is really going in the refined direction. It's somehow opposite to the unrefined direction. And it is this aspect which should be relatively new. And purely mathematically, the main result can be viewed as construction of quasimodular forms satisfying non-trivial functional equations starting from built-in numbers of moduli spaces of one-dimensional current sheaves on P2. So if you have pure algebraic geometry, you can make sense of this statement. We consider moduli space of sheaves, look at built-in numbers, construct generating series out of them in a slightly strange way, and the output will be some quasimodular forms satisfying non-trivial functional equation.
Pierrick, two questions. First, there's a bit of a hiss. I don't know if you have some idea what it seems to be correlated with something you're doing, but so double check that.
Okay, I will try to
okay.
avoid moving too much.
I think we can live with it, but if there's some obvious cause, we might want to remove it.
Okay. So I will try
okay.
to...
The other question I wanted to ask you is, you will tell us what you mean by the refined topological string, I hope.
Yeah. Obviously. Sigma just an overview, and now I explain the plan, what I will talk about. Yeah, obviously. Yeah, so the plan, I will just start in fact with a review of maybe things that many people here know, which is just ordinary topological string, ordinary holomorphic anomaly equation, then refined topological string, refined holomorphic anomaly equation. And then, so what I mean there precisely for my purpose. And then the main statement, which will be mathematical derivation of the refined holomorphic anomaly equation for local P2 and then the Nekrasov-Shatashvili limit. So essentially, my definition of a refined topological string will be in terms of like a refined Gopa-Kumar-Varfa invariant count defined geometrically as count of M2 branes. But I will say much more about that. So here, just an overview. So this thing will be the main result. And the main idea will be a reformulation of this Nekrasov-Shatashvili limit of the refined closed topological string in this example on local P2 as an open topological string on a different geometry, a kind of dual geometry. And the proof of this reformulation will involve a scattering diagram reformulation of the Kontsevich-Soberman wall-crossing formula in tropical geometry. In particular, even if the topological string is mainly about curves, in this story, we'll really need to consider the full D4-D2-D0 BPS spectrum. And once we have this reformulation in terms of open topological string, the proof of the refined holomorphic anomaly equation will be on the open string side using some connection via some degeneration argument to the closed topological string. And as a corollary of this story, we'll get a new formula relating the unrefined topological string and the Nekrasov-Shatashvili limit of the refined topological string, which will be a theorem for local P2 and which will be conjecture to hold for all local del Peso surfaces. So this thing is a plan, and now I start from the very beginning. So I start by some overview of the topological string from first some kind of physics perspective. So fix X a Calabi-Yau threefold. Then from coupling an appropriate twist of the two-dimensional supersymmetric sigma model of target X with two-dimensional topological gravity, we can define A and B models of the topological string. More precisely, for every genus G, you get genus G amplitudes, which are obtained by integration over the moduli space of genus G Riemann surfaces. So this topological string depends on some parameters. So we have a moduli space M of parameters, which is a complex manifold. For the B model, M is a moduli space of complex structures on your Calabi-Yau. And for the A model, it is a stringy complexified Keller moduli space of X. And genus G amplitudes of the topological string are function Fg on the moduli space of parameters. So I wrote Fg of T and T bar, where T and T bar are holomorphic and anti-holomorphic coordinates on the moduli space. The moduli space is a complex manifold. It makes sense to pick holomorphic, anti-holomorphic coordinates. And the genus G topological string amplitude is a function of these parameters. And some naive arguments suggest that this Fg of T and T bar should be some holomorphic function, so a function of T, but not of T bar. But in fact, it's not the case. As was shown by Bershadski, Cecotti, Odgo, and Varfa, there is a subtlety coming from the fact that the moduli space of genus G Riemann surfaces is not compact. And to get a compact moduli space from Riemann surfaces, you need to add nodal curves. And the holomorphic anomaly equation expresses the fact that the defect of holomorphy comes entirely from there. So schematically, the del bar of Fg, so which would be 0 if Fg were holomorphic, is expressed as a sum of terms, where the first term you should think about it geometrically as all possible ways to split a genus G Riemann surface in a genus I Riemann surface and a genus G minus I Riemann surface connected by a knot. And the last term is coming from a genus G Riemann surface with one self-intersecting knot. So here, the only thing which really matters is that the non-holomorphy of Fg is entirely determined by Fg prime for G prime strictly less than G. And the holomorphic anomaly equation is a very powerful tool to solve the topological string because it gives you a way to recursively compute Fg up to ambiguities, which are holomorphic functions on the moduli space. And often, if you know enough information about the boundary behavior of these holomorphic ambiguities, you can fix them uniquely because holomorphic functions are extremely rigid objects. Here are just some examples of such a thing. The A model of the quintic threefold was solved for G. Here there is a typo less or equal than 51 using holomorphic anomaly equation and known or expected boundary conditions. And something even stronger is true for the A model of some non-compact Calabi-Yau threefold such as local P2. In such a case, the A model is uniquely determined by the holomorphic anomaly equation and known or expected boundary conditions. So this thing was essentially a physics overview of the topological string and the holomorphic anomaly equation. Now I'm making some more mathematical remarks. The first remark is that if we focus on the A model, there does not exist yet a general definition, mathematical definition of what a stringy complexified Keller moduli space attached to a Calabi-Yau threefold X is. In the case when you know mirror symmetry for X, when you know mirror Y for X, then there will be a definition as a moduli space of complex structure on Y. But a priori, you don't know how to define it. And the related fact is that there does not yet exist a general mathematical definition of the genus G amplitude Fg of T and T bar. What exists mathematically is a power expansion around the large volume limit point, T equal plus infinity, of some holomorphic limit of the genus G amplitude of the topological string. More precisely, if T is a linear coordinate on the complex around cohomology of X, which is a good approximation of the stringy Calabi-Yau space near the large volume limit point, then there is a way to make sense of this holomorphic limit where T bar goes to 0, where you extract from the in general non-holomorphic topological string amplitude some holomorphic object. And now this holomorphic object, if you expand it in power series, it has a mathematical definition, where the coefficient of its expansions, n g beta, are number of holomorphic curves in X of genus G and of class beta. So they are defined by enumerative algebraic geometry, and more precisely, they are the so-called Gromov-Witten invariants. So from a purely mathematical point of view, what you can do, you start with X, and for every G and beta, you solve a problem in enumerative algebraic geometry, you count some curves, you get some numbers, and then you define fg of t as this power series. And from this mathematical point of view, it's not at all clear that fg of t, for example, has a non-zero radius of convergence. But of course, the physics, the fact that there should be this globally defined object fg of t and t bar implies that this mathematical series fg of t should have non-zero radius of convergence, and much more should have some analytic continuation to the universal cover of the moduli space. And the fact that fg of t and t bar, which is a globally non-holomorphic object, the fact that this thing exists, predict that the holomorphic part should have a quasimodular-like transformation with respect to the action of the fundamental group. So one way to rephrase this statement is that fg of t bar is a globally defined object on the moduli space which is non-holomorphic, but you can encode the same information as a holomorphic object, which will not be globally defined, but will only be globally defined up to some monodromy-like transformation. And then the holomorphic anomaly equation for fg and t bar can translate into an equation describing how this holomorphic object fg of t failed to be strictly modular. So here I've stated some mathematical result, which will be in the case which is relevant for us, which is the case of local P2. So from a physical point of view, this theorem was predicted by Aganagich, Boucher, and Clem. And the fact that it is a mathematical statement where you start with a definition in terms of Gromov-Witten invariance has been proved in various ways by Honglu Fan, Low Pandey, and Kautzi-Itani. So the statement is that for local P2, this non-compact Calabi-Yau threefold, the generating series fg of Gromov-Witten invariants are, after an appropriate mirror map change of variables, quasi-modular forms for the congruent subgroup gamma 1 of 3 and satisfies the expected holomorphic anomaly equation. So what is, again, non-trivial in this result is that at the beginning, fg of t starts as a formal power series, and part of this claim is that this power series converges given the holomorphic functions. And not only that, but in fact, this holomorphic function is a quasi-modular functions. And furthermore, the quasi-modularity aspect is described as the holomorphic anomaly equation. Here I should make some remark, which is why this kind of result is maybe not so easy as it might seem, which is you might think that after all, the A model of Gromov-Witten invariance of toric Calabi-Yau threefold, so local P2 is an example of toric Calabi-Yau threefold. After all, it's solved. You can consider it as solved by the topological vertex formalism. However, the subtle point is that it's not known how to deduce quasi-modularity result and holomorphic anomaly equation directly from the topological vertex. So even if for every given degree, every genus, if you want to compute a number, you can use it using the topological vertex, it's not clear how to deduce this general property, quasi-modularity and holomorphic anomaly equation from it. Okay, so this thing was my short review of topological string, holomorphic anomaly equation. And here I just stated the mathematical result in the very particular case we care about, local P2, where essentially the expected physics result have been proved. And now I start going towards the refined topological string. And for that, I recall the embedding of topological string in M theory. So it has been argued by Kopakuma and Vafa that the genus G A model amplitudes on the Calabi-Yau threefold compute particular supersymmetrically protected terms in the low energy effective action of type 2 string theory on the 10-dimensional background Minkowski space in 4 dimensions times your Calabi-Yau. And then using the strong coupling limit of type 2 string theory is M theory, you can obtain an M theory description of the topological string. And the output is this formula where you take the sum of all possible genus of your genus G amplitude Fg of t, and if you introduce a string coupling constant Gs, and you sum as a formal pair series, it admits a very different looking description, where here the important object, this is H beta, which is some space of BPS states for M2 branes of charge beta, which is a vector space and which is a representation of the 5-dimensional little group SO4, whose universal cover is SU2L cross SU2R. So via the connection with M theory, your topological string admits a description in 5-dimensional terms in terms of BPS states in 5 dimensions. These BPS states have some left spin and right spin, and then you construct generating series out of that. So here you have a trace of H beta, and you have a parameter Q, which remembers the left spin of the BPS state. And the Q parameter on the BPS side is related to the string coupling constant GS versus non-trivial correlation, non-trivial change of variable Q equal E to the power IGS. So in this formula, you only remember the information about the left spin of the 5D BPS states. And so you can get a refinement by remembering both the left spin and the right spin. So the physics definition, or one physics definition of the refined topological string is as follows. You replace a trace over the Hilbert space H beta, rather than to have Q to the 2kGL, you introduce two parameters QL and Q right, and you consider QL to the power GL and Q right to the power GR, where GL and GR are the left spin and right spin of your BPS states. So you consider this right-hand side, and you expand it formally by doing this change of variable. So you have on this formula, you have Q1, Q2, QL, and Q right, and you express it in terms of this parameter epsilon1, epsilon2, and doing this exponential change of variables, you formally expand. And doing this expansion, you defined this Fg1, G2 of t. So here I should stress the logic. Before Fg of t was defined independently by topological string, the connection with M theory was expressing Fg of t in terms of these BPS states. But now we refine the story at the BPS states level, and then by formal change of variables and expanding back, we define the amplitude Fg1, G2 of t. So here, just a comment, how you recover the ordinary story is by setting epsilon1 equal to minus epsilon2 equal to IGS. And so what I denoted Fg1, G2, if you put G1 equal to 0, if you consider F0G, you recover the ordinary topological string Fg. And let's say from the physics definition, you expect these functions Fg1, G2 of t to be convergent objects, and in fact to come from a globally defined function Fg1, G2 of t bar on the moduli space of parameters. So here, some slightly subtle point is that Fg1, G2 of t and t bar does not have obvious worldsheet definition. And in particular, there is no BCOV-like derivation of a holomorphic anomaly equation for it. So for ordinary topological strings, there was a physics geometric derivation of the holomorphic anomaly equation from the picture of the boundary of the moduli space of genus G Riemann surfaces. But now we have this object Fg1, G2 depending on two parameters, and they have been defined through some non-trivial change of variable from the refined BPS story, and not from some worldsheet-like definition. So it's not clear that you should expect something like a holomorphic anomaly equation. Nevertheless, a refined form of the holomorphic anomaly equation was essentially guessed by Krefel and Ulrer and Wang and Clem, and it has a form arrowed there. So the prediction is that the non-holomorphicity of this series FG1, G2, again, will be completely determined by what happened for FG1 prime, G2 prime, where the pair G1 prime, G2 prime is in some sense less than G1, G2. So this formula has exactly the same form as the ordinary holomorphic anomaly equation, except now you have two parameters.
Remind us, how do you define G1 and G2? What are they in terms of?
Yeah. So the point is here, I have essentially, by this formula. So G1 is like the power in the expression in epsilon1 plus epsilon2, and G2 is the power of the expansion in epsilon1 times epsilon2. And epsilon1, epsilon2, they're obtained from the Q1, Q2 parameter by exponential change of variable.
Okay, and in particular, at the topological string point, you just set G1 to 0 everywhere, right?
Yeah, I just say that the ordinary topological string is like epsilon1 equal minus epsilon2, which is like setting G1 equal to 0. Yeah, but somehow it will be the key point of the story that says G1, G2 parameter apparently do not have an obvious geometric meaning. They are the coefficient of the expansion in epsilon1, epsilon2, and the expansion in epsilon1, epsilon2 is taken from the refined BPS expression in terms of the Q parameter by some formal change of variables. And for the ordinary topological string, Fg admit to more direct worksheet definition as the genus G amplitude. But for general G1 and G2, actually you do not have such interpretation. But as I said, despite the fact that you do not have an obvious worksheet justification for refined holomorphic anomaly equation, you can just try it. And essentially it worked, which means that first this refined holomorphic anomaly equation is as good as in the ordinary case, which means that for things like local P2, like non-compact Calabi-Yau threefold, since this equation with known or expected boundary conditions uniquely fixed this function Fg1, G2, this refined topological string. And the notable fact is that you can check the answer against different definitions of the refined topological string. So is that the one coming from gauge theoretic partition functions or the refined topological vertex? So there are various predicted ways to compute the refined topological string, and you can check that the answer you get from the refined holomorphic anomaly equation and what you get from this other answer agree numerically when you compute explicitly low order terms, which tend you to believe that the refined holomorphic anomaly equation is indeed correct.
So remind me what Huang and Clan did. They also fixed the holomorphic data, and then the equation determines the rest, right?
Yeah. So the claim is that there are enough information about boundary conditions. So here I did not say, but I wrote a list like large volume behavior, orbifold regularity, conifold gap. There are enough conditions which uniquely fix the holomorphic ambiguities.
Okay, and you need more data than in the unrefined case? Or
yeah, I mean, so I guess, I mean, amongst these conditions, the one which is the least trivial is, I guess, a thing called conifold gap condition, which tells you if you look to the behavior of this function Fg near the conifold point, then this function has a pole of some order, and then the subleading term should be regular, which would mean that all subleading pole, all the coefficient of subleading pole should be 0. Which is something which I guess does not have a very strong justification, but appears to be true in many examples. And for the ordinary topological string, you use that, and for the refined topological string, you use the analog of this statement. That all the Fg1, G2 still satisfy this property. Yeah, and so here you use various things. For example, you use the fact that near the conifold point, you know leading term. You know the refined form of the leading term, for example. Yeah, but the general claim is that once you exploit all this kind of boundary condition data, then you can uniquely fix the holomorphic ambiguity at each step. Like there are enough equations. And so some of the recursive procedure given by the holomorphic anomaly equation has a unique solution in the refined case. Okay, so here in my survey of the physical definition of refined topological string, I made this comment about M3, M2 branes. So now to go back to mathematics, I need to say slightly more about it. So the space of M2 branes H beta should be some kind of cohomology of some moduli spaces of D2-D0 branes, which mathematically are moduli spaces of current sheaves supported on curves. So something like holomorphic curves, a Riemann surface in your Calabi-Yau with a holomorphic line bundle on it. This thing will be a geometric description of a D2-D0 brane. Then you look to the moduli space of such object, and then its cohomology. And then it's expected that this cohomology should be essentially the space you want, the space of BPS states of M2 branes. And then you should be able to recover this SU2L cross SU2R action from the geometry of this moduli space. So for now, we'll not say more about it. So essentially, it's just the vague picture I just described is due to Gopal and Vafa. And to make it mathematically precise, it's quite subtle because these moduli spaces in general are singular algebraic varieties. And there is a long story about how to make it more precise.
I think physically and mathematically, you would expect that the sort of a better definition of what you should mean by it is essentially the Donaldson-Thomas theory, right?
Okay, so you might want to define.
With 1d6 brane.
Yeah, that's right. So one alternative way you might want to define is to consider the D6, D2, D0, so Donaldson-Thomas theory. That's right. But still, if you want to define your numbers from there, you need to do some kind of rearrangement or generating series. Like the numbers you want are not on the nose equal to the Donaldson-Thomas invariance. You need to consider generating series of Donaldson-Thomas invariants, argue their rational functions, and the coefficient of this rational function as a number you want. So indeed, it's a perfectly valid way to attempt a mathematical definition. And then it's a conjecture in general that is agree with the kind of definition I've just described there.
I mean, really, I think physically there isn't a really definition that goes along with it, right? The D6, the phrasing in terms of Donaldson-Thomas theory is better because physically also it's obvious that you're computing an index. So you're computing, it's more easy. You can state it. Not trying to be at the mathematical level of rigor, but just physically, what partition function are you computing? For the directly Gopal-Kumar Vafa theory, you would be trying to compute M theory path integral, and we don't know how to do that. Not really.
Yes, but still in the original Gopal-Kumar Vafa paper, there is some description of these. Of what should be the M2 theory answer in terms of these D2-D0 branes. So if you want, it's some kind of Donaldson-Thomas theory, but of slightly different flavor, like without the D6 one. And obviously the two should be related. And I'm adopting this particular point of view because for the refined story, the mathematical version I will adopt will be closer to this one. But obviously you can try to follow some refined DT path, and then it will be a conjecture that it agrees with the definition I will adopt. Okay, so here I just wrote again the definition and the statement of the refined holomorphic anomaly equation. And so here The main difficulty is that the refined holomorphic anomaly equation is a recursion over this parameter G1 and G2. But FG1, G2 is only defined through the non-Churchian variable Q1 equal exponential epsilon 1 and Q2 equal exponential epsilon 2. And so without some geometric or worldsheet-like interpretation of this parameter G1 and G2, it seems very difficult to prove anything. So for the ordinary topological string, the genus G is a genus, and so it has a clear geometric meaning. When you thinking genus by genus means looking to Riemann surfaces of a genus. But here it is not clear what it really means to consider FG1, G2. And so a related fact is that it's not known how to deduce quasimodularity and holomorphic anomaly equation from the refined topological vertex. Here you might argue that for toric Calabi-Yau threefold, maybe you can compute this refined topological string, for example, using the refined topological vertex. But still, it's not known how to go from there to the expected quasimodularity and holomorphic anomaly equation. So in this talk, we'll focus on the Nekrasov-Shatashvili limit, which is a particular limit of the refined topological string, which is in some sense orthogonal to the unrefined one. Nekrasov-Shatashvili limit, you set one of the two parameter epsilon 1 and epsilon 2 to 0, and you call h bar the remaining one. And then in this limit, the previous formulas simplify a bit. And in particular, our BPS index arc object is a trace of something, but now the dependence on the left spin and the right spin is only through the sum of the two. And so here the claim is that this thing is in fact a refined 4D BPS index for D2-D0 brane. So in general, you should consider 5D BPS states, which are a representation of SU2L cross SU2 right. But the claim is that in the Nekrasov-Shatashvili limit, this thing reduces to a 4D count of D2-D0 brane, where you only remember the diagonal SU2 into the 5D SU2L cross SU2R, which can be viewed as the 4-dimensional SU2. So here what remains is just count of D2-D0 brane in 4D with spin. So this omega beta of y is really some kind of refined BPS index which encode your D2-D0 4D BPS spectrum with the information about the spin, which is in the variable y. And so roughly mathematically, this omega beta of y is roughly the irreducible coordinates of the moduli space of D2-D0 brane. So just some combination of odd numbers of the moduli space, and for our purposes later, in fact, it will be only the polynomial of Betti numbers of your moduli space. So the thing which is slightly subtle is that if you want a fully refined story, then to get SU2L cross SU2R from the moduli space of D2-D0 brane is not enough to know the moduli space. You need to use a fibration structure on this moduli space and to exploit its fibration to get the 5D information. But the point is exactly in this Nekrasov-Shatashvili limit, this extra information is not necessary, and the answer has a purely 4D description as a refined count of D2-D0 branes. And in this particular limit, you can see what the refined holomorphic anomaly equation is saying. And it takes this very simple form. In particular, in this NS limit, the loop term of the ordinary equation has disappeared. So in general, you need to sum up all the possible ways your Riemann surface can degenerate. You can either have separating nodes, which separate your surface into two pieces, or it could have a self-intersecting node. And here the term with the self-intersecting node is not present in the NS limit. Because in the general formula, in the last term, you always decrease the second genus G2. So this formula is not symmetric in G1 and G2. You only decrease the G2 terms. And in the NS limit, the G2 is already set to 0, so you can no longer decrease it, and this term is not there. A slightly maybe fancier way to say it is that if you think of the holomorphic anomaly equation as being satisfied by some kind of wave function, then here this FG-NS limit satisfies an equation that we would expect for simply a generating function of a Lagrangian, so a kind of classical object. Okay, and so the main result of this talk, so which was essentially on the physics side conjectured explicitly by Wang and Clem, is that for local P2, the series FG NS of T, which are defined in terms of Betti numbers of some moduli space of D2-D0 branes, so mathematically some current sheaves on P2, they are quasimodular form for the group gamma 1 of 3, and they satisfy the expected refined holomorphic anomaly equation. So now we'll say a bit more about the precise mathematical definition of an object which enters our definition of FGNS. So here I wrote again the definition. So we need to define this omega d of y. And then from omega d of y, you write this formula, you expand y as exponential of h bar, and then expanding in power of h bar, it defines you the series Fg of ns. So mathematically, what you are looking for every d and chi, you consider md chi a moduli space of D2-D0 branes, which is mathematically a moduli space of semi-stable current sheaf on P2, which are supported on curve of degree d, and which have holomorphic color characteristic equal to chi. So the typical example of such a thing is a line bundle supported on a degree d holomorphic curve inside the projective plane. And d is roughly the d2 charge, the degree of your holomorphic curve, and chi is roughly the d0 charge, something like the degree of your line bundle on your holomorphic curve. And it's a very natural moduli space in algebraic geometry, which in fact has been defined and studied long ago for purely algebraic geometry motivation. Because if you simply fix a holomorphic curve, and if you look to all possible line bundles over this curve, you get the Jacobian, which is one of the most classical objects in algebraic geometry. And what we are doing is simply moving the degree d curves along all possible degree d curves in the projective plane, and over each of them, look to the Jacobian. So in fact, this moduli space is a family of Jacobian parameterized by the linear system of degree d curve in the projective plane. And the reason why the topology of this moduli space is non-trivial is that a degree d curve in projective plane can become singular. And so the moduli space of sheaves on it can become complicated. The Jacobian, which in the smooth case is a nice torus, when the curve singular, this nice torus degenerate into some singular complicated thing. So generically, you have a nice
the connection to the Jacobian. It was too fast. I did not get this.
Yes. So in fact, MD chi has a map to the space of curves of degree d in P2, which is just a projective space. And the fiber over a point in the space of curves is isomorphic to the Jacobian of this curve, if the curve is smooth, because it's a set of all possible line bundles that you can put on your given holomorphic curve in P2. So if you want, it is some, I mean, there are many ways to say it, but it's like some Hitchin-like system picture where you have some vibration, or Sabel-Witten-like picture.
Oh yeah, no, this makes sense, right? Can you say what would you do differently if you do you know which question should one ask to get the analogous version with both parameters where we keep track of both?
Yeah, that's so. So in fact, let me first say that in this NS limit, what we'll care about will be omega d k of y, which is essentially the Poincare polynomial of this moduli space. So just Betti numbers of this moduli space. But in general, to get the two parameters, you really need to use this map from this moduli space to the moduli space of curves. You need to use this vibration structure. And the suggestion, which was in the original Gopal-Kumar-Farfar paper, it was one of the SU2 is like some SU2 coming from action on the cohomology coming from the basis of this vibration, and the other SU2 is coming from the fiber of this vibration. And here in this NS limit, the only SU2 which we remember is a diagonal SU2, which is just a natural SU2 acting on the cohomology of the total space, which does not need reference to the vibration structure. And which is why it's really some 4D object, which only needs the moduli space of D2-D0 branes without this extra structure that you will need to recover the full two-parameter invariance. And which is fundamentally why the story I'm describing is in the NS limit, because it's simpler in this sense. Yeah, so in some sense, you could just have started with D2-D0, counting D2-D0, refine BPS index, and we are saying something about these numbers. But of course, all the previous story predicts that if you organize them in this particular generating series, define FGNS in that way, then this thing should be quasimodular and should satisfy some version of the holomorphic anomaly equation, which is maybe not completely obvious if you just start with a 4D D2-D0 point of view. Okay, so mathematically, we define this omega d of chi as just Poincare polynomial, so just some polynomial in Y where the coefficient are Betti numbers of your moduli space. And there is some slightly technical fact, which are in general, these moduli space are singular. So if the moduli space is smooth, you consider ordinary cohomology. And if the moduli space is singular, you consider so-called intersection cohomology, which is some cohomology theory which is better behaved for singular spaces. For example, it always satisfies Poincare duality. And in fact, from a physics point of view, it's reasonable because when the space is singular, what you mean is that you should really look at the smooth locus, which correspond to like strictly bound states. And then when you try to quantize this moduli space, you should look to something like L2 cohomology of this space. You should need to impose some kind of, this space is not compact, because when you want to compactify, you add marginally bouncing, and then you need to impose some natural L2 conditions. And intersection cohomology is some algebra or geometric gadget, which often coincide with these more maybe physical natural L2 conditions. So in first approximation, these omega d chi and y are just constructed from Betti numbers of these moduli spaces. So this moduli space M d chi is smooth if GCD of d and chi is 1 and is singular in general.
So
here is some, yes.
Is this claim that the singular points don't contribute to that based on some conjecture that there are no marginally bound states, or
so
in the full quantum theory, it just
yeah. So I did not say that the singular points were not contributing. So essentially, there is like two slightly different points of view. Like maybe one point of view where you only consider, well, I would guess maybe strictly bound states. And in some cases, the moduli space of such a thing is compact. And then you just take ordinary cohomology. Or in some other cases, it's non-compact. And when it's not compact, you need to be careful how you define the cohomology. And just quantum mechanically, the fact it's not compact is not a problem. You just want to look at things satisfying some kind of L2 condition. But with the appropriate metric on this non-compact part. And the claim is as to compute this L2 cohomology of the non-compact part is the same thing as computing this intersection cohomology of the compact object, which is singular. It's just two ways to transfer the information, to encode the information.
But do we know that that is actually the same as the partition function of this D2-D0 bound state, or?
Yeah, so here for my purpose, I will define this omega d chi y as the Betti number for the intersection cohomology of these moduli spaces. And I think it's maybe in general open question, like maybe you want to compare that with other definition that you might have of the D2, D0 index. But I claim it is one reasonable definition.
Can you remind us what chi is?
Yeah, and exactly, I will say more about chi in one moment. Chi is some kind of D0 charge. It's like geometrically, I mean, it's like the holomorphic Euler characteristic of your current sheaf. Or in more concrete way, if you think about the line bundle on the degree D curve, it's like the degree of this line bundle. Yeah, so I will exactly arrive at this point, which is in the formula I wrote there, on the top, I have omega D without chi, because after all, we want a count of M2 branes, and the count of M2 branes only depends on this homology class D. Well, naively, when you talk about D2, D0 brane, it seems you have this new parameter chi, which is how many D0 brane you have. But the conjecture is that omega D chi only depends on D and not on chi. So what is clear is that if you fix a degree D curve and look to the space of all possible line bundle on this curve of a given degree, you always get the same answer. You always get the Jacobian. Because if you look, ordinarily the Jacobian is the space of line bundle of degree 0. But it's isomorphic to the space of line bundle of degree 1. Because you can take a line bundle of degree 0 and twist by a line bundle O of P, where P is a point on your curve. And get the isomorphism between the space of line bundle of degree 1 and line bundle of degree 0. So at the level of independent curves, this kind of statement is like not surprising. It's like you can add a D0 or remove a D0 without changing anything to your moduli space. But here, our moduli space MD chi is constructed from all possible curves in P2, and it's not completely clear how to make such a choice of points, like which D0 brane you need to add in a uniform way. And in fact, MD chi, the moduli space, really depends non-trivially on chi. So in fact, I just said that MD chi is smooth if D and chi are coprime, but if singular if D and chi are not coprime. So certainly the moduli spaces are not isomorphic in general. Nevertheless, the conjecture is that if you look to the Betti numbers of these two moduli spaces, and Betti numbers in the correct sense if the moduli space is singular, it should be independent of chi. And somehow this thing is necessary if somehow if the connection with M theory makes sense, because in the M theory you do not see chi, you only see the M2 charge. And so I don't know how to prove this conjecture, but here are some theorems which tell you that it's like a weak version of this conjecture, which says that this omega D and chi only depends on D and GCD of D chi. And I claim already this statement is not obvious at all. You can have different chi and chi prime, such that GCD of D chi equal GCD of D chi prime, but still the moduli space MD chi and MD chi prime are just not isomorphic as algebraic variety. So the obvious way to prove this statement, which is to prove that the space are the same and so they have the same Betti numbers, just cannot work. So you need to do something more. In fact, the only proof I know of this statement, in fact, will use a full story I will describe and ultimately uses some Gromov-Huygens theory, which is a slightly strange story where you prove a basic looking fact on topology of moduli space of curves and will use some Gromov-Huygens theory type arguments. So for now, we can forget about this conjecture. And for what follows, I will simply define omega d of y as some kind of average of omega d chi over all possible of chi, all possible values of chi. So what is easy to see is that MD chi is isomorphic to MD chi plus D. So there are only finitely many values of chi which matters for a given D. The conjecture is that all these finitely many values are equal, and I don't know this conjecture, so I just take the average of these numbers. This thing is mathematically the precise thing which will enter in my definition. So here I wrote the formula again. So now I say a bit more precisely what omega d of y is. It's constructed from Betti numbers of this moduli space of sheaves supported on curves in P2. They are polynomial in y. Then you write down this right-hand side. You do the change variable y equal exponential of h bar. You expand in parity of h bar, and you define f, g, and s as the coefficient of h bar to the power 2g minus 1. So this thing is a mathematical definition of f, g, and s, taking as input these moduli spaces of D2, D0, or if you want one-dimensional coherent sheaves on P2. And now I've written the theorem again, which is that this series f, g, and s, after appropriate mirror map, they are quasimodular forms for the group gamma 1 of 3, and they satisfy the expected refined holomorphic anomaly equation. Okay, so from a purely mathematical point of view, what is really strange is this change variable y equal exponential h bar. Because at the beginning, omega d of y is some kind of Poincaré polynomial. Just look at Betti numbers, and y, the power of y is just a cohomological degree. So omega d of y is very natural from a mathematical point of view, just a Poincaré polynomial. It's not clear at all why mathematically you should do the general y equal exponential h bar and then expand in power of h bar to get something interesting. But what the previous physics story predicts is that if you do that, you define f, g, and s, and then this series f, g, and s are quasimodular and satisfy the refined holomorphic anomaly equation.
I think this perspective, I might be wrong because I haven't thought about these things for a long time. But the perspective of D0, D6 might actually be helpful in understanding what one is doing. So in other words, go to the other string theory frame where it's obvious that you're computing an index. And I think what you're doing is you're explicitly setting to 1 the parameter that keeps track of the D0 branch charge. I think that's what that limit turns into. So you would naturally average over all numbers of D0 branches explicitly. And what you should be computing is something like one D6 brane with arbitrary number of D2 branes partition function. And that's the thing where y keeps track of the spin. I think that's what this is.
Yeah, it could be, but I'm not sure. Yeah, it could be. Yeah, I think it's true that starting from some refined DT theory, you would naturally define some omega d of y in a way which only depends on d without seeing any extra parameter. I think it's correct. Yes. Yes, that's right. So this thing somehow it's a so if you like the D6, D2, D0 story, and there are various mathematical definitions of this refined D6, D2, D0 story. And then it's a conjecture that it agrees with what I've just defined in terms of D2, D0. In fact, even for local P2, these conjectures are just open. I mean, it's not. Okay, so here I'm repeating myself. I say the main issue for something like proving some holomorphic anomaly equation for this fg of ns is that the g does not mean genus. Whereas in the usual holomorphic anomaly equation, the g means genus, and it's a kind of recursion on the genus. So here the strategy for how to prove this theorem would be to find some kind of genus interpretation of fg ns. So we like to interpret fg of ns as some genus g worldsheet object. And this genus G object cannot be the unrefined topological string, because in general, certainly for local P2, your G is at least once is FG and S, it's just different from the unrefined FG. So here is some int, which is slightly formal. You just stare at the formula which defines FG and S, which is slightly strange looking coefficient 1 over k squared and 1 over y to the k over 2 minus y to the minus k over 2. And then you compute the derivative of that with respect to the t parameter. So essentially you just bring 1k down. Now you get 1 over k times 1 over y to the k over 2 minus y to the minus k over 2. And here the kind of formal observation is that the structure on the right-hand side is exactly the expected BPS structure for the open topological string, unrefined, honest, open topological string, as predicted by Augury and Varfa. So just this formal observation tell you that it should make sense to try to interpret the derivative of FGNS as some open topological string. And the main claim, one of the main claims of this talk is that for local P2, or more generally for local del Peso surface, it's possible to identify what this open topological string is. So here I'm starting describing a different geometry where the open topological string will live. So maybe for one moment, we should forget about local P2 and just start from scratch and defining a new geometry, which will be closely related, but will not be local P2. So here I just recall some standard looking toric geometry. If you start with a projective plane P2, you can view it as a T2 fibration over some triangle. So if you look to P2, it has a T2 Hamiltonian action. If you look to the corresponding moment map, you get this torus fibration structure on P2 where the fiber of a point in the interior of a triangle is a 2 torus. And at the boundary of the triangle, this torus degenerates to a cycle. And at the corner, the full 2 torus degenerate to a single point. So you can view P2 as having a fibration of a triangle, and over the interior of the triangle, it has a smooth fibration in torus. In fact, over the interior, what you get is just C star squared, a complex torus inside P2, which admit a trivial torus fibration over the interior of the triangle. Now the geometry we'll care about is some modification of this picture, where you replace the boundary of the triangles, so the 3 lines, you replace them by something smooth. So you smooth your triangle into some kind of disk. And geometrically, what was before above the interior, it was a complement of a triangle of lines in P2, it was C star squared. And now we replace these 3 lines by a smooth cubic curve, an elliptic curve. And so now what is above the interior is what I call U. It's a complement of a smooth elliptic curve in the projective plane. And it's a non-compact Calabi-Yau surface. So if you take P2, and if you remove a triangle of lines, you get C star squared, which is a non-compact Calabi-Yau. And if you smooth this triangle of 3 lines into a smooth cubic, the complement is another non-compact Calabi-Yau, which is no longer C star squared. And before C star squared has a trivial fibration in T2, and this new geometry U admit a T2 fibration with 3 singular fibers.
Sorry, I didn't understand. So we know local P2, so it's some sort of compactification of C star squared by the 3 lines that correspond to the edges of the triangle.
Yeah, that's right. Yes.
Okay, so what are we doing now?
Yeah, so I consider now. So I prefer to view it in the other way. The previous picture views C star squared as a complement of the union of 3 lines in P2.
Sure.
Now I consider a new geometry U, which is a complement of a smooth cubic in P2.
And a smooth cubic is an elliptic curve. Yeah, okay.
Yes, a smooth cubic is an elliptic curve.
Do you have some insight? Why do we do this?
I will say much more in some moment.
Can I just try and
Yes.
get an idea of where we're going with this? Is the point just where you're saying that you can get a 4-dimensional quantum field theory either by a D3 brane probing this non-compact piece of a K3 surface, or by geometrically engineering this field theory on this local threefold? Is that the point?
Yes, it will be exactly the point. So the point is in this geometry, we'll simply look, maybe rather than 2B, I use M3 language, we simply take an M5 brane, wrapping one of these fibers. So, okay, maybe I just say it the other way around. It's quite expected just from string dualities that the theory you get by type 2A and local P2 should be the same thing as what you get if you look to the mirror of local P2, the kind of mirror curve. And if you take a M5 brane wrapping this mirror curve. And the geometry I'm describing here is exactly the mirror geometry, but after some apical rotation.
Okay, I'm sorry, I lost the statement. So can we just go more slowly? What is B, for example?
Yeah, that's fine. BB is in this picture, it's a kind of disk, the disk on this picture, like some base of some vibration.
It's a base of the T2 vibration. Sorry, it's some local piece of the of your U, or what?
It's like a base. So U has a vibration over B. There is a map from U to B
with T2 fibers.
With T2 fibers, and 3 of them are singulars. Are like nodal elliptic curve. Over generic points, the fiber is a T2. And there are 3 special points in B over which the fiber is a degenerate T2 with 1 cycle shrink to a point.
Okay, let's try it the other way. Since I don't know where you're going. Can you repeat your answer to Max's question? Your story was about an NS fibrane on the mirror of local P2 on the curve.
Yeah, that's right. So this thing is later, but let me just say it like that. So probably there's a mirror of local P2. You can think about the family of curves. Well, this family is whatever superpotential mirror of P2, and the fibers of this map are genus 1 curves minus 3 points.
Yeah.
And essentially, I will look to a compactified version of this mirror picture where you compactify these genus 1 curves. I will look to a mirror family, which is just a family of genus 1 curves. And then combination of string duality tell you should look to indeed some NS5 or M5 brane wrapping such a curve.
Okay.
But in such descriptions, the BPS states will come from M2 branes with boundary on this M5 brane. But if you check the kind of BPS condition, this M2 brane needs to be special Lagrangians.
I see. So what you're doing, I think, is there's a paper of Oguri and Vafa after Kontsevich and Sobelman came out, trying to explain what Kontsevich and Sobelman are doing in terms of a
exactly. I'm exactly
in terms of an fiber on a spectral curve. I see.
Yeah, exactly. And I have put reference to Cecotti and Vafa's paper. Yeah, so it's exactly.
Oh, Cecotti and Vafa, that's right. Not Oguri and Vafa.
Yeah, that's
okay.
right. Yeah, that's right. And but some other point is that in this description, the M2 branes are like, I mean, if your curve is holomorphic, the mirror curve is holomorphic. So the curve wrapped by the M5 brane is holomorphic. Then the M2 brane are special Lagrangian. But I would like a description where the M2 branes are holomorphic because you want to go to some topological string where you count holomorphic curve. So I want some apical rotated version of the mirror family. And somehow, what is special to local P2, and which I guess is new with respect to Cecotti and Vafa, is that this is a very particular example. You can identify this like apical rotated complex structure in which the mirror curve become Lagrangian. You can identify this complex structure with something explicit, which is what I'm just describing here, this complement of an elliptic curve in P2. So in general, if you start with a complex manifold, which has an apical metric, And if you look to a different complex structure compatible with hypercalametric, in general, the complex manifold can look very different from the original one, from the just complex geometry. And here what I'm describing is what you get after applying this hypercalametric rotation business to the mirror geometry. And for example, the fact that the mirror family has 3 singular fibers, that the potential has 3 critical points, translate into the statement that this torus vibration has 3 singular fibers.
So do you know which quantum field theory you're engineering? Is this 40, the SU2 and F equals 1 theory, or because I'm just guessing based on the number of singular fibers you have?
Yeah, I mean, something it's not really 40. I mean, it's like a type 2A. I mean, whatever. It's like type 2A and local P2. And it's, I mean, it does not have like a gauge theory description. I mean, it is some 4D n equal 2 theory, but I cannot say.
Yeah, this is probably more like a little string theory, maybe. Because you have 4 compact directions.
The spectral curve is, if the spectral curve is the mirror of local P2, right?
Yes.
Then that theory should be some 4-dimensional limit of the 5D CFT that you get from
Yeah, that's right.
on the local P2.
Yeah, that's right. Yeah, I mean, from local P2, you can construct the 5D CFT, and you can go to the 4D version of this theory. Yes.
Okay, but you don't know which theory this is?
Yeah, I mean, I don't think it has a like gauge. Like, you know, if you do the same thing for local P1 cross P1, then you get something like SU. You could just get an appropriate limit. You just get pure SU2 n equal 2. But for local P2, there is no. Yeah, like you do not get a gauge theory in any usual sense.
Yeah, these theories have super conformal points, right? Where the P2 shrinks.
Yes,
you get
yes.
a 5D super conformal field theory.
Yes. Okay, so yeah, I was trying to go the other round because I just wanted to describe directly the geometry where the open string is living. But indeed, one way to understand why this geometry is the correct one would be exactly to go through the step we just quickly describe. So as I said, we'll consider open topological string in this geometry. So counting Riemann surfaces with boundary on these T2 fibers. And more precisely, we'll do something which is done in this Chekhotiv-Afar paper, which is this twistorial construction, which is this U, this complement of an elliptic curve in P2. It's a non-compact Calabi-Yau surface with some complex dimension 2. It's holomorphic symplectic. But for ordinary topological string, you want a Calabi-Yau threefold. And so you cook up a 3-dimensional geometry by essentially adding a third direction, and we just call it C star. So you just consider U cross C star, but you twist the complex structure along the C star direction according to the hyperkähler structure. So the hyperkähler manifold U has a P1 family of compatible complex structure, and you consider C star inside it, and you consider the family over C star, you get some Calabi-Yau threefold geometry that I call a set. So all the holomorphic curve will live inside the surface U. But the full geometry is 3-dimensional. And so if you fix a point B in the basis of this vibration, you want to define some count NGV open of B, which would be some counts of genus G Riemann surface with one boundary, where the boundary has some class which live in H1 of the torus fiber, which is just some Z squared if you fix the basis of one cycle on your T2 fiber. So
What have we done? Have we just gone to the mirror, or mirror plus a hyperkähler rotation, or?
Yeah, that's what exactly, mirror plus hyperkähler rotation.
Okay.
Yes, exactly. So you would like to define the number NGV open of B. So you fix a T2 fiber and you count open curve with boundary on this fiber. In fact, these numbers jump as a function of the fiber. There is some wall crossing phenomena. And generally speaking, defining open Gromov-Wheeler count is mathematically difficult. For example, here this geometry is not toric, so you cannot use things like toric localization to give some formal definition of the open count, which is what people did to get some mathematical version of the topological vertex, for example. So here, the way to get a mathematically precise definition in the limit where B, so the point in the base, is somehow close to infinity. It's like close to the boundary of this disk, which means that our T2 fiber is closed from this elliptic curve E, which compactified our geometry U into P2. So we look to a limit where our T2 fiber is somehow close to the elliptic curve, which compactifies the geometry.
Sorry, what is B?
Yeah, V is like the class of the boundary of the curve.
I mean the little b.
A little b, it's a point on the base.
Mm-hmm.
B, so it's like which T2 fiber you are looking at. And in fact, if this T2 fiber is close to infinity, so in this picture close to this blue elliptic curve, then among the two cycles on your two torus, there is a particular one which is shrinking to a point when you go to the elliptic curve. In the same way that in a standard toric description, when you go to the boundary of the toric polygon, some cycles of your T2 shrink to points. And here the same thing, when you approach the elliptic curve, one cycle will shrink to a point. And I call 1, 0 this particular cycle collapsing to a point. And now if you have an open curve whose boundary wraps this particular 1, 0 cycle, you can just get a closed curve by gluing in a disk, touching the elliptic curve in one point. Because this cycle is shrinking to a point, you get a disk, and you can just glue there a holomorphic disk to get a closed holomorphic curve. So if you want this thing, it's just a mathematical trick to define the open count in the limit where the T2 fiber is really close to infinity, where you expect the open count to be just equal to this kind of closed count, where the closed curve touched the elliptic curve in only one point. And mathematically, there is a well-defined theory of holomorphic curve touching some divisor with some given constraints, which is called relative Gromov-Wheeler theory. And I use that to define these counts.
But the picture you're drawing here is before hyperkähler rotation, right?
So essentially, the picture is the same before and after. What is different is what is the type of the object which are drawn. So before, the T2 are like holomorphic, and the red curve are Lagrangian. But after, the red thing are holomorphic, and the T2 are Lagrangian. And somehow the geometry which compactify by adding the elliptic curve is only the one after hyperkähler rotation. Whereas the other one before hyperkähler rotation, the elliptic fibration, compactify in a completely different way by adding a singular elliptic curve at infinity, which is something a bit confusing, which is different complex manifold. Like the property of the natural compactifications can be very different, even if these two complex manifolds come from the same hyperkähler geometry. Like before hyperkähler rotation, from a complex geometry point of view, you have the elliptic fibration, like family of elliptic curve. In particular, from algebraic geometry, is not an affine variety. But here, after hyperkähler rotation, you have a complement of an elliptic curve in P2, and this thing is some affine variety. This geometry does not contain any compact holomorphic curve. So maybe I should just say this is very much more elementary example, just C star squared. after apical rotation, you can just get elliptic curve cross C. Right, C star square has a Lagrangian torus fibration over R2, and after rotation, they just become trivial elliptic fibration. And here, what I'm discussing is some kind of deformed version of this object, where elliptic curve cross C is replaced by this non-trivial elliptic fibration with the 3 singularities, which is a mirror geometry. And the hypercorrected version is not C star square, but this is deformed geometry complement of an elliptic curve in P2. And so here the upshot of what I just said is that if you look to open curve wrapping this particular cycle 1, 0, vanishing at infinity, you can get a well-defined mathematical numbers using relative Gromov-Witten theory. Another theorem is that these open count are exactly what we want. It's exactly the open topological string, which will produce the derivative of the FGNS series. So you have this equality. If you take the sum of a genus of the derivative of FGNS, the coefficient of H bar expansion are just this higher genus open invariance. And in particular, if you write the open side in the expected Honglu alpha BPS form, then this refined BPS count omega dy of D2-D0 brane on the closed side just become equal to the Honglu alpha open BPS state count. So from a purely mathematical point of view, you can say on one side you have some closed story, like just closed D2-D0 brane, refined with spin information. On the other side, you have some unrefined open story. And they agree. And at the formal level, the kind of expected BPS form of the open side matches, by what I showed previously, matches the expected BPS form of the FGNS side. Are there any questions about this statement?
Is the Nekrasov-Shatashvili topological string partition function supposed to agree with the unrefined one after some wall crossing? Because
So at the end of the talk, we'll have some kind of version of this. Like at the end of the talk, we'll really have a formula saying the Nekrasov thing and the unrefined things are related by some kind of explicit formula. But it depends by what you mean wall crossing precisely.
the reason I ask is there's the usual 4D, 5D lift that relates the unrefined topological string to Donaldson-Thomas invariants, and these sound like just I mean, yeah, what you're calling the Nekrasov-Shatashvili invariants are in the same yeah, you're counting D-brane bound states in the same string vacuum, so it seems like these should be related by some wall crossing.
Yeah, except I don't know how to make this statement precise. I'm not sure wall crossing with respect to which parameter. But in some sense, at the end of the talk, there will be some kind of formula which will be exactly in the spirit of what you just said. And maybe this formula has a more direct interpretation, but I don't know about it.
Okay. You probably want to get rid of the zero branes. I would also guess that the right-hand side is, if you ran this, Guyot-Moore and Ansky in principle have a way of, I think, calculating the BPS invariance from the spectral networks and such things. I think if you ran their prescription, that you would get these Nekrasov-Shatashvili ones, because I think that these zero branes are hard to capture there, or would be hard to capture.
Yes, so certainly you can imagine using some spectral network to compute this D2-D0 story. That means this invariance, D2, counting D2-D0 brains. And indeed, there have been some papers studying that, but like doing like explicit, like low degree computations. But I mean, and you can see the D0 in the spectral network point of view, but like, I mean, you can compute low degree example, but I don't know how to say more about it. I mean, and in fact, the picture I will describe will not be the spectral network story, but will be some kind of orthogonal picture. I will say more in one moment. But indeed, like if you care about these numbers, number of D2, D0 brains, I mean, they are just like BPS states of this n equal 2 4D theory. So you can imagine use the spectral network technology to compute these numbers, certainly. But I think for the particular purpose that I care about, I think this technology is not developed enough yet to prove the kind of thing I want. So here we're talking about D2, D0 on one side and some open curve on the other side. But in fact, this open curve is only one part of the open theory. It is the part of the theory you get when the cycle wrapped by the boundary of a holomorphic curve is this particular cycle shrinking at infinity. But there is another cycle on T2. There is like a basis of 2 one cycles on T2. So in this correspondence, we are only using 1/2 of the open topological string. And the more refined theorem is that if you use a full open topological string, if you use count open curve with boundary general 1 cycles on the T2, then it will match with D4-D2-D0 brains, where the D4 and D2 charges, which are like 2 integers, will map to the 2 integers which define the cycle, which is the boundary of a curve in the first homology of the torus. And okay, so here I stated again, and I think this is not an example of MNOP-like Gromov-Wheaton DT, but it's exactly, as Mina said, it's exactly the Chekoti-Vafa story. So Chekoti-Vafa in their paper wanted to have a physical derivation of the Kontsevich-Sauberman wall crossing formula for count of BPS states in the 4D n equal 2 theory. And they looked at the theory engineered by an M5 brain wrapping a curve, in which BPS states are given by M2 brain with boundary and M5 brain. And then they explain how to look to an appropriate, essentially they do an Aperkel rotation business and twistorial construction to get a Calabi-Yau 3 geometry, in which this count of open M2 brain will be related to open topological string. And then they argue on the open topological string side for why this thing should satisfy the Kontsevich-Sauberman wall crossing formula. And they do that using the connection between open topological string and quantum Chern-Simons. And essentially what we'll do will be essentially this story, but in like reversing the logic. So first, maybe I just repeat this Chekoti-Vafa story. It's a case where the full BPS spectrum of an n equal 2 4D theory, so is encoded by M2 brains, and so will be encoded by open topological string. So in the case where I look at type 2 and a Calabi-Yau 3-fold, the full BPS really means D4, D2, D0. Not just D2, D0, but D4, D2, D0.
In fact, I think you could say it like this. Usually, to replace, let's say, this local P2 by the B model mirror, we do 3 T dualities. To get to this picture, right, where you have an NS5 brain or an M5 brain or a D4 brain, you do 1 T duality. Well, 1 or 2, depending on which end you're coming from. So it's some kind of a middle description where you don't do full mirror symmetry on all 3 tori. But so going from the B model, you do 1, and going from the A model, you do 2 T duality. Then you get this NS5 picture. And I think that that's what you're describing. that's in fact, I mean, how, yeah, well.
Yeah, I think I agree.
Yeah, just to restate part of that, the Chakotay-Vafa thing was really relating to 4D n equals 1 D-brane theories, not 4D n equals 2 or 5D n equals 1, whatever dimension this is. But
no, I mean, this particular paper of Chakotay-Vafa 2009 is really n equal 2 4D. It's about the warp crossing of BPS states in n equal 2 4D.
Right, but the way that they're studying the wall crossing is by relating it to a 4D n equals 1 setup by compactifying on by studying a compactification which breaks half of the supersymmetry.
Yeah, in some sense it's kind of correct, because at the end you relate to some open topological string, and indeed from a space-time point of view, the open topological string is some n equal 2 two-dimensional theory. I don't know if it is what you mean.
They definitely wanted a D4 brane on the spectral curve or an NS5 brane on the spectral curve.
Yes.
Right.
Yes.
That's the theory they're studying. I'm just saying that when you say open topological string, they related it to the usual. They're computing a superpotential. They're not computing a prepotential. Anyways.
I mean, you're right in that what they're trying to count is the BPS states in that theory. And so those.
Yeah, I think I'm just saying that this relationship between this closed and open string picture that you're saying, I think goes back a lot longer than 2009. This is like a late 90s idea, I think. The relationship between the geometric engineering picture and the 5 brane pictures of 4D n equals 2 theories. This I don't remember the name of the paper.
Yeah. I mean, yes. I mean, certainly the fact that geometric steering on a Calabi-Yau 3 is the same thing as some M5 brane on a spectral curve. Yeah, certainly this thing is much older. I think what is specific to this paper is his translation going from M2 to M2 brane with boundary on M5 and relating that to the topological string. It is this step which is done in this paper.
Yeah, the open topological string on the twistor space.
Yeah, that's right. Yeah, that's right. The fact that the BPS spectrum is given by count of open M2 brane, I agree, this thing is much older. But the fact that you consider this twistor space to relate this open M2 to open topological string on this twistor geometry is what is contained in this paper. And then somehow they use this topological string interpretation to prove what they want, to then connect with Chen-Simons and then derive the expected wall crossing formula, which is something which is not clear if you just start with the open M2 picture, which is difficult to understand anyway because it's an M theory and it's not so easy. Okay, so here, in fact, on this side, probably there is what we just discussed in various ways. Maybe in one order or the other, that if I start with the bottom of this slide, you can do mirror symmetry, you get the mirror geometry, and then you do some apical rotation and you get this geometry U. And if you follow what happened, you start with a current sheaf on your local P2, which becomes special Lagrangians in your mirror geometry, and after apical rotations, they become holomorphic curves. And if you are careful, you can see where the closing has become open. Yeah, essentially you have open thing is a two-dimensional geometry, and when you consider three-dimensional mirror, which is like UV equal W, and when you lift these open Lagrangian, they become closed Lagrangian in dimension 3. So essentially, yeah, I guess here there is roughly like 3 steps. One, which is kind of mirror symmetry, then with some kind of 2D, 3D lift. Yeah, it depends if you talk about mirror symmetry of P2 or mirror symmetry of local P2. And the two are related by this kind of 2D, 3D lift, and then hyperkähler rotation.
Yeah, as Max said, these last two steps, or this kind of perspective on sort of doing mirror symmetry midway is very, very old. It goes actually to the very earliest papers of Kummerin on cyber-Witten theory. So it's like 95. It's really old.
Yeah. So I guess I agree. And I guess the only part which is new in this step is for local P2 is the hyperkähler rotation, and the fact you can identify explicitly the result of the hyperkähler rotation, which is complement of an elliptic curve in P2.
I mean, like you can actually calculate something there. That's totally new.
Yeah. That's what is that you can use this open M2 picture. Yeah, that's what. The fact you identify the answer for hyperkähler rotation is like you know where to look for holomorphic curves. Whereas before looking for special Lagrangian is like more difficult.
So you're computing the BPS spectrum in the sort of infinitely weak coupling limit because you're sitting at this point at infinity.
Yes.
Can the same relative Gromov-Witten techniques be used to study the interior chambers or no?
Yeah, so just in one moment to go to the proof, we'll need to go to the interior. But to give a mathematical definition of this open count, it only works in this weak coupling limit, where you can close the open curve into a closed curve. If you want some honest mathematical definition of the open count in the interior, you should do some honest open Gromov-Witten invariance.
So setting aside definition though of what you're computing, can you compute them in the interior, not just via wall crossing from infinity, but directly?
Yeah, I mean, essentially, we'll compute them by wall crossing from the interior. So we'll have a definition for the thing near the boundary. And yeah, so you see in this theorem, I wrote almost theorem. Again, I wrote for any reasonable mathematical definition of the open invariance. Yeah, so it's just a question, like, yeah, so let's say, I guess at the moment, I don't know a general mathematical definition of this homogeneous open invariance in the interior.
Oh, okay, so let me ask a related question. The invariance, the open invariance here that you're defining will only agree with the Nekrasov-Shatashvili partition function if you're studying the point at infinity, right?
Exactly. So I should have been more careful when I say Nekrasov-Shatashvili limit count D2-D0 states. There are really D2-D0 states in the large volume limit from a geometrically point of view. And the claim in this statement is that the count of D2-D0, or more generally D4-D2-D0 in the large volume limit are equal to this count of open curves with boundary on the torus, which is really close to infinity.
Okay, so this relationship between the 4D BPS spectrum and the Nekrasov-Shatashvili limit, it is only holding because we're at this point at infinity in moduli space.
I think so. I mean, somehow the NS object in its definition, I guess, is near some large. In this like geometric definition, starts near the large volume limit.
Okay, thanks.
Yeah. So exactly. So I know how to relate the NS partition function and D2-D0 near the large volume limit, more or less by my definition. And this thing agree with count of open curve with boundary on the torus really close to infinity. But then somehow the next step will be to go away from this point. And it will be the next step. So to prove this theorem, we'll go away from this point and we'll do wall crossing. But in the connection between like BPS spectrum and NS partition function, I only know it at the large volume point at infinity.
So for the invariance to calculate, how complicated is the dependence on the D4 branch charge?
Very complicated.
Very complicated.
Yes, it's like on P2, it's like the So like D2-D0 were just curves supported on a curve in P2, but now if you have D4, it's like something like vector bundles on P2. And it's like studying vector bundles on P2 of higher and higher rank. Like D4 charts, each has a rank of your vector bundle on P2. And
so if you were in this correspondence with Donaldson-Thomas theory,
yes.
At large radius, the dependence on D4 brane charge was actually supposed to be really, really simple if you have one D6 brane there. Because what makes it simple is that from perspective of 1D6 brane, all we are doing is just tensor it with some line bundle, which doesn't change anything interesting. Of course, if there wasn't for the 1D6 brane in the DT theory, then it's getting very complicated, and in fact, you have a complicated phenomenon and so forth. So
yeah, that's also, so it's exactly the point. Yeah, I do not have a D6.
I
really
but wasn't this supposed to correspond to something that still did have a D6 brane? In that on the DT side, I think, okay, maybe one should just calculate more carefully what it is that you're computing. But on the D6, D4, D2, D0 side, I would have thought that this Nekrasov-Shatashvili limit is simply setting the D0 brane charge to 1. And so we would have still had D4, D2, D0, and D4, D2 branes and 1 D6 brane, plus actually any number of D0 branes, we just don't keep track of the charge.
Yeah, that's right. But in this story, somebody fix 1 D6 once and for all, right?
Yeah, but as soon as you fix 1 D6 once and for all, there changing the number of D4 branes was supposed to be simple because you have 1 D6 brane.
Yeah, and I think I agree with that. Yeah, I agree.
So what kind of so I think this correspondence between DT theory and the computations you're doing should have gone through. So maybe one has a puzzle, or we still don't, one doesn't understand.
Yeah, I mean, certainly the story I'm going to describe, I do not see the D6. I never see the D6.
Sure.
And I don't know where the D6 is supposed to be.
Yeah, you wouldn't see it because it's there by, you see, in the D6 brane picture, it's manifestly you're computing an index. That's what the D6 brane picture does for you. Yes. It's manifestly a trace of, around the circle of some count. You've gotten rid of that circle that makes the fact that when it's computing an index manifest by sort of relating M theory to type trace string theory in a different way. But the invariants should not change, but by how you compute them, or how you look at them. So
certainly the invariants I will look at, they have wall crossing phenomenon, like with respect to the Keller moduli. Is it the same thing if I have 1 D6? Do we also have non-trivial wall crossing? Yeah, I guess it's another thing I'm slightly confused. Usually when people call about 1 D6, it tends to stay near the larger volume.
No. In fact, you can very easily compute it inside the modular space. In fact, we had a talk just last week about this. Then you get a modular of quiver framed quivers, and it's very easy to describe other points in the modular space as well.
Yeah, that's right. Yeah, that's right. So I guess both have wall crossing. So both should be related in some way.
Yeah.
But I don't know the general relation at the general point.
And it's easy for you to compare the different points in modular space. Somehow the orbifold point is the very symmetric point where.
Yes.
Interesting. It's really interesting. Okay.
Yes,
I think that the most wonderful thing is you can actually calculate something.
And one way you can calculate will just come soon. I mean, just as an orbifold point, in D6 there's some kind of frame quiver representation. And just without D6, I guess you just have ordinary quiver representation, like without framing. Like D6 is something like the framing, and you just forget the framing. And I mean, it should be the kind of numbers I compute, I guess. But I agree there is a basic point that in my story I never see the D6, and I would like to understand better where the D6 is.
Yeah, usually these things are very hard. I mean, string theory makes precise predictions, but one can sometimes get confused if you don't have enough computations to actually check what you're saying. Mm-hmm. Now with enough computations, it could become a very interesting story.
Yeah, so
it is a very interesting story.
Yeah, so here is, okay, I don't know if it was obvious from the previous chain of dualities, but I claim this is B, which was our base of our T2 vibration, if you go through the chain of duality, it should be related to the stringy Keller moduli space of local P2. And if you go precisely, I claim it's exactly some 3-to-1 cover of the stringy Keller moduli space of local P2. The usual stringy Keller moduli space of local P2 has like one conifold point and an orbifold point of order 3. And if you take a 3-to-1 cover of that, you just orbifold point becomes smooth. The conifold point becomes 3 conifold points. And this geometry with 3 singular fibers can be identified with the basis of these T2 vibrations. And I claim if we go through the chain of dualities, you can understand that on the mirror side, it's just because like when you write UV equals W, you can think about the place where your UV equals 0 happens, depending on which point you are on the base. So it makes clear that the base can be viewed as a complex moduli of the mirror. And so by mirror symmetry, this base should be some Keller moduli space on the other side.
Pierrick, can I ask a question? So for the genus 0 part, actually the open Gromov-Witten invariance, I actually defined it earlier. So
yeah, exactly. That is your definition.
Genus 0 part, how much this BPS states can recover?
I mean, what do you... Yeah, so, I mean, on the whatever, like D2-D0 language, it's like taking the unrefined, maybe I should not call it unrefined, but it's like setting y equal to 1 for getting the spin information.
Mm-hmm.
So when you do that, the full NS object, which just reduces to just the genus 0 part, which is just the same thing as the genus 0 part of the unrefined story. It's like just a pre-potential time. Like. So from the point of view of my story, this thing is not really interesting. I mean, if you only remember genus 0, you just look to F0 NS. But F0 NS is just equal to F0 unrefined. So it is just equal to closed genus 0 Gromov-Witten theory of local P2,
mm-hmm.
which is like known in many ways.
I see. So higher genus is important.
Yeah, so in my story, to see some of these interesting like FGNS, all the information is about the higher genus.
I see. Thank you.
So obviously, if you want to compute genus 0 numbers, I mean, in fact, they are still interesting and you can study them. But for the point of view of this talk, it's really crucial that you consider this higher genus because it's exactly the parameter in this FGNS expansion. Okay, maybe now I should just have picture. Yeah, so okay, we have this chain of geometric relations, but now I actually want to prove mathematically that my count of current sheaves on P2 is equal to this kind of open holomorphic curves. And now, how am I going to do that? So I'm going to do essentially to argue that the same algorithm compute both sides. And roughly the same algorithm will be some version of the Kontsevich-Soberman wall crossing formula on both sides. But the way it will appear will be quite different. So maybe I start with a holomorphic curve side. So you can't open holomorphic curve in a T2 vibration. You can just look to some kind of projection of this holomorphic curve on the base. And in some appropriate limit or tropical limit, this kind of curve will become some kind of tree on the base. And here the picture you should have in mind is that each of these 3 singular fibers somehow create one holomorphic disk. Like there is a vanishing cycle at each singularity, which is some kind of basic building block for holomorphic curve. And then you construct more complicated holomorphic curve by gluing together these initial objects. And so at the end of the day, you will have picture made of trees whose initial roots are at the 3 singularities and then which combine in various ways to produce more complicated curves. And now the question is, how do you get numbers out from such tree picture? And the claim is that you can, that this combination of holomorphic disks to construct more complicated curve is governed by the Kontsevich-Soberman-Wall crossing formula. And this thing is exactly what Cecotti and Varfa argued in their paper. And the way they argue it is using the connection between open topological string and quantum Chern-Simons. And because I don't know how to establish this correspondence mathematically, the way we derive the fact that these numbers satisfy the wall crossing formula is essentially by some combinatorial tropical argument. So you need to prove that indeed counting such a curve is the same as counting these kind of trees with appropriate multiplicities. And then you check that the data of these multiplicities on the trees is equivalent to the Kontsevich-Soberman wall crossing formula. So here I'm skipping a lot of details, but the basic idea is some kind of tropical geometry ID. You want to count holomorphic curve. In some torus vibration, you look to the base of this vibration. In some appropriate limit, you are counting some kind of trees. And then there is some algorithm telling you if you know to count curves contributing to edges coming to a vertex of a tree, you will know how to compute the numbers attached to the outgoing edge by some explicit formula. So here it was a sketchy formula, a sketchy picture where I only have a tree with only one vertex. And here is a picture of the honest formula for local P2. So maybe I come back to explain what this picture is. Here I have the basis with the three singularities. And then what I'm going to draw, I'm going to remove the small disk in the middle, like something like near the orbifold point, I'm removing the disk. I get an annulus, and I take the universal cover of that. So when I do that, my three singularities will lift to infinitely many singularities, which are placed on this parabola here. So this picture, what it is a drawing of all possible projections in some appropriate tropical limit of all possible holomorphic curves in the T2 vibrations.
But I thought we wanted to have them end on the torus.
Yeah, that's right. So you should think, so torus is like a point in this picture. And so in general, if you fix a point somewhere on some ray, then like the tree is made of rays in this picture and ending at this particular point correspond to holomorphic curve with boundary on this particular torus.
And what will give you? So you had this y. You had the generating functions that contain this y variable.
Yes.
So what happens to that?
Yeah. So here on the open topological string side, you just count genus. I mean all possible genus. You sum over genus h bar to the power 2g minus 1, and y is exponential h bar. So indeed here from the open topological string is something which is not that clear. You sum over genus, but at the end of the day, everything will be like polynomial in the variable y equal exponential h bar.
And is there some sense in which the things that you're counting look like large disks plus sort of degenerate genus, higher genus contributions, or they basically will look like? I guess you'll have breathing more. Yeah. No. In
general, not really. Except the way you're able to prove something, but some of these trees decompose into like vertices. And what happened at a vertex is simple enough so that you can compute it explicitly. And for the very simple vertex, what happened is some kind of genus zero, like pair of points, genus zero thing. And all the higher genus thing are like cover of this genus zero picture.
Okay.
And here you do some explicit computation. And when you do this explicit computation, you see this y variable appear from the h bar variable. So here to prove this correspondence, the idea is that you have some holomorphic curve, and then this holomorphic curve in some appropriate limit breaks according to a tree, and then you study what happens at each vertex of the tree. So the tree can be very, very complicated. This picture is really very complicated. But at each vertex, the picture is simple enough so that you can compute it explicitly.
So do you get some kind of a tropical vertex where you have a vertex contribution that sums over higher genus? I didn't quite understand. You probably, I mean, I'm sure you said it, I just didn't understand it.
Yeah, so this picture is with some algorithm where there are initial rays, which are the rays like on the bottom, which are rays decorated by explicit generating functions. And once these two rays crosses, there is a scattering algorithm. So you need to add new rays, which are somehow obtained by scattering of these two initial rays. And the quant series suborbital algorithm tells you exactly which generating function to attach to these new created rays. And then you iterate. The new ray then can intersect other rays and so on. Maybe another way to say it is that this picture is, okay, one way you might think about it is some kind of 4D spectral network. If you think as a spectral network as living on a moduli space of 2D theory, and where intersection of a spectral network being given by the 2D Chekhov alpha wall crossing. And yes, this picture is living on a moduli space of 4D series. And when the things are crossing, you apply the 4D wall crossing formula. It's one way to think about it. Okay, so some other claim is that this same picture with the same initial data and the same algorithm will compute both the open topological string and the D2-D0 D4 sheaf picture. And on the open string side, it happens because this thing is some kind of tropical picture, the holomorphic curve degenerate into these trees. And on the sheaf side, this picture is really drawn in the stringy Keller moduli space. And these trees are closer to the attractor flow picture of DNF and DNF Moore. So from the BPS side, these rays are the loci in the space or in the stringy Keller moduli space, where there exist BPS states with the given phase of the central charge. In fact, for the precise picture I'm looking at, purely imaginary central charge. And in fact, this picture is really a picture of the stringy Keller moduli space in very particular coordinate, where the coordinates are given by the real part of the central charges. So that all these lines are really straight lines, and it's really easy to draw. You do not have to solve any differential equation. So the claim is that this picture is a picture of a stringy Keller moduli space with particular coordinates, and these trees are exactly loci where there exist BPS states with purely imaginary charge. And the generating function are count of BPS states. And the initial objects in this algorithm are simply the line bundle O of n. So the pure D4 object, which become massless at the conifold point. So the initial object of this picture, they are like the conifold points, which emit some D4, just the line bundle O of n, which are the simplest possible D4. And then everything else is reconstructed by wall crossing.
So the pure D4 plane is the horizontal line? So you say your coordinates are...
That's right. Yes, that's right. The line bundle of n, they are like, yes, the horizontal line and more generally the tangent to the parabola. They are the initial rays of the picture. And we know the BPS degeneracy because there is one line bundle, so we just count one. And then everything else is reconstructed by this algorithm. So if you want, it's some kind of fancy version of the well-known mathematical fact, the derived category of sheaves on P2 is generated by line bundles. So it means any objects in the derived category can be obtained from line bundles by doing a lot of exact triangles in the derived category. And this picture is some kind of explicit way at the level of cohomology of a moduli space how this thing happens. And here, so here, the point that even if you're only interested in D2-D0, which is what we really care for this NS story, in this algorithm, you need to study D4 anyway, because when you go away from the large volume limit, the D2-D0 decay into D4 bar. And the initial data of the algorithm are D4. So you need the full D0, D2, D4 story, even if you only care about the D2-D0. Yeah, and so if you want like independently of the NS stories, this picture is just like a new algorithm to compute D0, D2, D4 on local P2. Okay, and maybe I've already speak a long time, so yeah, I just wrote the statement again. So essentially, here the thing to remember is that somehow this picture has two completely different interpretations. In one picture, it's like some tropical version of the holomorphic curve. On the other picture is some kind of flow in the string Kähler moduli space describing wall crossing of BPS states. And because the same picture is the same with the same initial data, with the same wall crossing formula, the two invariants in the large volume limit we care about are the same. It is what the mathematical proof is of this relation.
This is how Kontsevich and Solomon imagined that formula in the first place, right? From the wall crossing of these disks in K3, or I mean, in geometries like that, right? So the fact that two coincide is
yeah, in some sense, yes, exactly. Like the history of the birth of the wall crossing formula is exactly that, like disk in mirror symmetry and then BPSs. Yeah, so the fact that that's what. So it's not so surprising in this sense, except in general, it's not clear how, given one situation, how do you find a dual description, like given.
Sorry, what's not clear?
I mean, in general, if you apply, like you have like two different realizations of the wall crossing formula in terms of disk or in terms of BPS states. And like given one realization, it's not clear how to find the other one, if the other one exists. But anyway, and something else related.
Don't you right now have a machine that works for all Tor Calabi-Yau?
Okay, so I claim what I'm doing here will work for all local del Pezzo surfaces.
Why not more generally?
But not, I guess, for example, not a toric, even something that could seem like much simpler, like the conifold, whatever. I don't know to say anything but conifold.
Why?
Because it has to do with this identification of this explicit hyperkähler rotation. And okay, I know how to do that only for local del Pezzo. Maybe there is a much more general story, it's possible. But I expect the story as I described to be exactly the same word by word, only, okay, I expect it to be exactly the same for all local del Pezzo, toric or not. But I don't understand it well enough to say that it will apply to any toric Calabi-Yau 3, for example.
And that's surprising.
Yes, I mean, somehow it has to do with that in this identification of the hyperkähler rotated geometry, it's really P2 minus the elliptic curve. So for any del Pezzo, there is a version of that, just del Pezzo minus an anti-canonical divisor on the del Pezzo. So, and here the fact that it's toric or not does not play any role, but beyond that, it's not clear to me.
Oh, so can I maybe? Oh, sorry, I didn't mean to.
No, so sorry, you can ask.
So yeah, I just want to understand how this, okay, so the last few slides you were explaining how to prove that this open string context satisfies the Kontsevich-Soibelman wall crossing formula using the tropical combinatorial picture.
Yes.
How does that then give you this theorem?
Yes, because then on the sheaf side, the Kontsevich-Soibelman wall crossing formula is satisfied by general, whatever, Donaldson-Thomas theory. So both sides somehow satisfy the same wall crossing formula. And so the only need to check is that you have the same initial data.
What is it?
This scattering diagram picture is one way to organize the information nicely so that the initial data is only what happens near the conifold point. And near such a point, you can match explicitly the two things because both are really simple.
Near the point at infinity, that's where you match them, or?
No, you match them near the conifold point, so really in the interior. And the point you care about is a large volume.
You're one of the singular fibers.
Yes, exactly. Yeah, so it's the point. The comparison between the two sides is easy near the singular fibers.
Near any one of them?
Yeah, I mean, in fact, yeah, the three of them are symmetric. There is some Z mod 3 symmetry between them.
Isn't that weird if you have a moduli space with 3 singular fibers, but you're one of, like, yeah, you know, the light BPS states coming from the hypermultiplet ending on that single guy.
Yeah, that's right. And you might say maybe it's not enough because there is this lighting, but maybe there are many other BPS states.
Yeah.
Is it what you are?
Yeah, absolutely.
Yeah, exactly. So exactly, this picture is not a naive application. If you are doing some naive version of a scattering diagram, we would like to find a point where you know the full BPS spectrum, and then you will move from this point applying the wall crossing formula.
Yeah,
right?
so how do you know the whole BPS spectrum near one of the singular fibers?
Yeah, so here's the tricky thing. You do not know the full BPS spectrum near one of the singular fibers. But on this picture, you only draw BPS states with purely imaginary central charge.
Okay.
So you only look at each point, you only look to a very particular subset of the BPS spectrum. And the claim is that near one of the singularity, if you look to the BPS states which have purely imaginary central charge, then you know what they are. There is only this light hypermultiplet.
Okay.
And the claim is that just knowing that and drawing this picture is enough to reconstruct everything else in the large volume limit. So somebody the point that this scattering picture is, it's not like naively applying wall crossing, finding a point where everything is known and moving from that. Because in fact, for local P2, probably there is no point where everything is simple. But the idea is to organize the information according to the phase of the BPS states and only draw the picture of BPS state with a given phase. And if you care about what happens in the large volume limit at one point, where maybe the phase is not purely imaginary, you can always move, staying near the large volume limit where the phase is purely imaginary without any wall crossing. And then this picture tells you what the number is. So, yeah, certainly I agree. Somehow it's one of the main points why this thing is like different from like more naive application of the wall crossing formula is that here the information is organized according to the phase of the central charge. And somehow it's a key point. And here it's key that this picture will only look simple for this particular choice of purely imaginary charge. Like for example, nothing in this picture go towards the orbifold point. The orbifold point would be somewhere in the big white middle. And nothing goes there for this particular choice of phase. So you could draw this picture for any possible choice of phase of the central charge. And the claim is that if you do this particular nice choice, purely imaginary, then you get this nice picture.
So I guess more generally, you'll get a version of this just living in higher dimensional space, right? Because you'd have a genus G curve and not genus 1. So everything's going to get more complicated, but.
Yeah, so. Okay, so certainly this picture from BPS point of view, certainly should hold in any dimension. Just look to the base, whatever, Coulomb branch, string Euclidean moduli space in higher dimension, and you can draw this kind of picture. In general, there will be like codimension 1. Yeah. Walls, and suddenly you can draw this picture. And suddenly it's expected that, in general, it's expected that this picture will correspond to count of curves in the moduli space. So in general, it will be something like in the Seiberg-Witten integrable system. And certainly for counting curve of genus 0, this thing is pretty much expected. And maybe, in fact, maybe even known in some cases. But this higher genus story, okay, I think I'm really confused about counting higher genus curve in higher dimensional spaces. Because naively, mathematically, the expected dimensions go wrong. So in short, certainly the dimensions go wrong. Like a dimension of moduli spaces of curves. At least in the naive way. So I think I'm pretty sure there should be a nice way to do something more correct, which will produce a correct answer. But yes, so certainly there's a big part of this picture which should generalize to drawing thing in higher dimensional Coulomb branch and counting curve in like higher dimensional integrable system. And here the picture I'm describing is some kind of low dimensional case where there's some kind of coincidence between
Right.
geometry and the really space-time geometry. They happens to agree for some low dimensional coincidence.
Right.
But yes, certainly you expect such a thing in general. Okay, so now I will just essentially conclude. So to the main point, you go from the sheaf side to this open string side. And then to prove quasimodularity and holomorphic anomaly equation, you work on the open string side. And this open string side is obtained by counting holomorphic curve in P2 relatively to the elliptic curve E. And then you do, essentially you push this E at infinity to try to relate this geometry P2 with a divisor E to just local P2, just the starting geometry without any divisor. I guess what I'm trying to say is that you can consider local P2, closed curve on local P2. But what we care about are like open curve in P2 minus E. But now both of them are count of holomorphic curve. Both of them are like Gromov-Witten invariants. And then you can relate them by some geometric argument. Like you can push the elliptic curve at infinity. You can stretch it in some appropriate way. The closed curve on local P2 will break into the open curve you want. In fact, other kind of open curve mapping to the elliptic curve. And at the end of the day, you're able to get just a concrete formula, where Fg is an unrefined topological string on local P2. It's equal to the Fg refined topological string is the NS limit plus correction terms. And the correction terms are given by Gromov-Witten theory of the elliptic curve. So remember here on local P2, there's just local P2, no elliptic curve. Here it's an open count in the complement of an elliptic curve. So in very rough terms, the difference between P2 with an elliptic curve and P2 minus elliptic curve is the contribution of the elliptic curve itself. So in this explicit formula, you have contribution of Gromov-Witten theory of the elliptic curve. But this thing is something which is known in essentially closed form by some old computation of Okounkov Pandey. They are like explicit polynomials in Eisenstein series. So these things essentially are known, and you get the explicit formula which relates these two orthogonal limits of the refined topological string. And as far as I know, this formula was not known before. And but once you know that, you use the fact that we know quasimodularity and holomorphic anomaly equation for the unrefined topological string. You use the fact that you know quasimodularity and holomorphic anomaly equation for Gromov-Witten theory of the elliptic curve. And combining these two statements, you get the desired quasimodularity and holomorphic anomaly equation for these FGNS.
Just to be clear, this last slide and this slide, we're talking about the relative, we're relating relative Gromov-Witten theory to normal Gromov-Witten theory.
Exactly.
That's what's going on.
Some appropriate degeneration argument. Like properly it's degeneration to the normal cone along E. Like you break P2 into a copy of P2 and a P1 bundle over the elliptic curve. And you follow how the curve behaves in this degeneration. Like your closed curve on P2 will become curve on P2 relatively to the elliptic curve, glued to curve in the P1 bundle over the elliptic curve. And after further work, this thing can be reduced to just curve mapping to the elliptic curve. We just produce Gromov-Witten theory of the elliptic curve as some difference between the relative and normal.
Describing this gluing of two disks into a closed curve in just in relative Gromov-Witten theory terms?
Yes. Yeah, that's right. So in fact, in relative Gromov-Witten theory, you only have like closed curve. You have a closed curve, we just break into two closed curve glued at a knot.
Does this work very generally for relative Gromov-Witten theory, or is this relying on the details of P2? Like, would this work for a 4 torus?
Yeah. So in fact, in this particular paper, there is a very general relation, which if you have X variety, any dimension, like smooth projective variety, D a divisor in X. You might try to relate ordinary Gromov-Witten theory of the line model O minus D over X to some kind of local geometry. You might want to try to relate that to the relative geometry of X versus the divisor D. And there is a general degeneration. You can go from 1 to 0 there. And what is specific to local P2 is that you can compute explicitly the correction terms in almost closed form. So certainly this kind of degeneration argument to relate relative and not relative Gromov-Witten theory is used a lot in many different contexts. And you could use it in a much more general context, but here the point is that you get something you can compute everything explicitly. And I guess for now, sorry, I'm already over time, so I will just stop there. Thank you.
Yeah. Thank you so much. This is wonderful. I wonder if so there was another sort of place where ordinary and Nekrasov-Shatashvili limit of topological strings somehow clash together. In this work of Marino on spectral theory, on associated with these spectral curves that arise from topological strings. I wonder if your results could not explain it, but my comment is way too weak to be concrete. But
I think I have no. Yeah, that's what in the story, like the NS thing is like some usual perturbative version of the quantization.
Yeah, somehow he needed.
If you want to get some non-perturbative thing, you need to add extra term, which are the usual.
Which is the Nekrasov-Shatashvili, yeah. Which is a very strange sounding story. So I think.
Yeah, that's right. And yeah, I do not understand the relation. But yeah, I mean, certainly I do not understand this relation. I mean, yeah. As far as I know, there is no reasonable explanation of this. Marino.
The class of theories that he studies are precisely the ones for which your formalism does work. So,
yeah, I agree with that. Yeah.
So I'm sure that that somewhere in your stories and the thinking about these lines is an explanation of what Marino is doing, and we're just his story is beautiful, but it lacks any kind of explanation of what's actually going on.
Yeah. Yeah, but I think even at a simpler level, like just the perturbative part of Marino, I mean, just the facts.
No, actually, sorry. So I still don't understand. Why does that? I see. So for you, you were just breaking up disks in this new geometry.
Yeah.
And then the Gromov-Witten side for you, the closed Gromov-Witten, was the closed Gromov-Witten of P2 itself, not O minus 3 over P2, right?
No, in fact, O minus 3 over P2.
Oh.
Yeah, in fact, it's really local P2. Yeah, I did not.
Where
yeah,
did
in fact, you break P2 into two pieces, and then you also generate O minus 3 over P2, which also break into two non-compact geometries. And it's really important to do that. So yeah, it's really local P2. It's not P2. It's really local P2.
Because you have them. You want the total Calabi-Yau.
Yeah, you really want the Calabi-Yau. Yeah, not some Fano like.
I see. Okay. So your ability to calculate the sums of these tropical looking BPS states, is this limited to these Fano surfaces? Is that some understatement, or? Does one understand how to do these counts more generally?
Yeah. I mean, you can do this kind of picture on any base of any kind of elliptic fibration. You just have simple initial array, and each time they meet, you apply some explicit conservative manual crossing formula, and you can compute things. Except in general, this picture just become very complicated, and it's not clear how much you can compute and how useful it is. Just happened in my story, just knowing that this algorithm exists somehow is enough for me to translate from one geometry, the geometry of sheaves, to another geometry, the geometry of open holomorphic curve. But just as a computational tool in low degree, you can do that much more generally.
And how about trying to bring in this variable that we want set to 0 to go to Nekrasov-Shatashvili limit?
Yeah, so I tried a lot, and I don't know how to get the second variable. So I'm saying you see the unrefined thing is just counting closed curve in local P2. The NS limit is counting open curve in P2 relatively to this elliptic curve. And you might ask, are there other intermediate geometry in which counting curve could produce the full refined topological string?
I think maybe what I'm confused by is whether we set the zero brane charge to 0 in doing this, or we sum over all the zero brane charges. But either way, one is doing something with a D0 brane charge, and what one needs to do here is put in other curves that don't that are maybe less obvious in terms of they don't look like simple disks, but they are whatever. Maybe they don't end on the Riemann surface. I think there are other kinds of curves. The question is just what's the mirror of a D0? What's this kind of a mirror of a D0 brane?
I don't think it's really D0 brane, because if you want to get the full topological string, just thinking in 4D D2-D0 term is not enough. To recover the full 5D BPS spectrum, you need to do something more. In some sense, the story already captures the full refined spin content of all D2-D0 brane. I guess what I'm trying to say is that this NS limit as a description as part of the 4D BPS spectrum.
I mean,
but for
okay, so let me ask you this: for just the space of BPS states, how many charges do you keep track of in doing this? 2 or 3? 3?
It depends what you mean by it. Okay, so in the full algorithm construction, you need D0, D2, D4.
But in these counts that you're doing here, in terms of curves ending on the spectral curve, of this ending on a spectral curve.
Yeah, that's right. This thing corresponds to curve with boundary on the spectral curve. And yeah, there is 2 parameters, the 2 cycles.
Yeah.
Which roughly correspond to the D2 and D4.
Yes.
But the D0 is not I mean, if you restrict to D2, D0, the D0 is not interesting, I guess, by the kind of statement I said, because it should come from M2, and so.
It's possible that it just means refining the count that you already have, but keeping track of something that you're not keeping track of right now.
Yeah, it's possible, but I'm not sure.
Yeah, I think one just has to go carefully through the dictionary. It shouldn't be that hard to understand. Well, I'm not sure that it's easy to fix it up, but to understand at least which question one should ask.
Yeah, because I mean, what is special about it, and I think that the dictionary really go to the 4D theory. But if you want the full thing, I don't think you can go easily to 4D. You need to stay to 5D in some way. I mean,
okay, maybe it's related to this confusion about the relation to DT theory.
Yeah, that's what, because even in the unrefined case, the relation to 4D, simple relation to 4D is not direct, but through the D6, you relate to 4D, to some kind of 4D. But for the general kind of thing I want, I don't know how to
But yeah, this does sound like sort of a different 4D, 5D limit that only works in the large volume limit. In the sense that you're relating to a different.
Yeah, that's why. So yeah, that's why. Yeah, the claim which is used is simply that the count of M2 brains in the NS limits, they just become count of D2, D0 brain in the large volume limit. This thing is one claim, which is what I use to go from this NS limit to the 4D BPS spectrum story.
Which means averaging over the zero brain charge, right? You don't keep track of it.
I don't think it means like conjecturally everything is independent of D0. For this particular D2, D0. Yeah, I agree. On the DT side, it will be the opposite. On the DT side, the D0 will be all the interesting thing going on.
We certainly know what we are losing, right? Because we know the full answer for local P2. So.
Yeah, sure, yes.
Okay.
Yeah, so maybe one way to say it is that like the unrefined thing, we know it's related to like DT, D6, D2, D0. This NS limit is related to D2, D0. But what the general thing is related to, I don't know.
No. We do know what the general thing is related to. In terms of D6, D2, D0, we do know that.
Yeah, that's what.
We do know that. The two parameters that you have is precisely the D0 brain charge and the spin, which is basically your Y variable.
Yeah, that's what. You can refine the D6, D2, D0 to get the full thing. I agree.
Yeah,
but the question is, how does it help to, for example, find a dual worldsheet like open topological like description? And this thing, I don't know.
I mean,
anyway, I think in your story there's a lot of new information, so that's great. I'm sure one can make also further progress there. So it's really great.
But yeah, it does seem like once you have an interpretation in terms of BPS states in the type 2A geometric engineering picture, then you must be able to reinterpret it in the open string picture via the usual relationship between class S geometric engineering and M5 brain pictures.
Yeah, that's right. And it's essentially what is happening in this talk. With the addition that you use this open topological thing as like a tool to really address this count of M2 brain and to get some kind of algorithm to compute it. But then I agree exactly. It's exactly the point. Once you are in the 4D BPS world, then you use this non-connection. Exactly. But if you do not take this NS limit, I don't know to go. Yeah, you could go to the 4D BPS with a D6, but without the D6, I don't know. And when there is a D6, I don't know how to go to some open topological string picture. Yeah, because let me just say something which is maybe obvious. Here I have the open topological string, which is unrefined. We could refine the open topological string. Yeah, and ask what does it correspond to? And I guess I'm just confused about this question.
I think that's somehow not the right thing to ask there. Okay, well, maybe we need to think a little bit.
Yeah.
But thank you so much for a really wonderful talk and a great story.
Thank you.
Yeah, thanks.
Okay. All right, thanks for joining us.
Yes, thank you again for the invitation. And sorry if it was slightly confusing at some point.
Oh, no, it's a wonderful story. This is, well, I think we like to have a sort of very informal format, so this is deliberate.
Yeah,
Thank you so much.
thank you.